By the way, Seattle is the best place to live during July, August, and September because it's 80 degrees, sunny, no humidity, beautiful. And there's mountains and ocean. It's incredible. But the reason it sucks in the winter is because this is what winter is for like 5 months. It's like just above freezing. It's always raining. But that means it's really green.
I was just going to say, the one plus is they have 3 temperate rainforests like right next door.
Yeah. Oh, it's incredible. I would totally take 5 months of this. But that means it's snowing in the mountains. So it's awesome. All right. It sounds like there might be some discrepancy on the exam on one of the questions. I just posted the answer key before class. So I will sit down and work through the problem. It's the one about Ka, Q versus K. Will the reaction make more products or make more reactants?
Oh, yeah. And scratch off.
Yeah, and just so I caught up with Justin after the exam, and he told me, oh, don't worry, like, we got it all, like, the scratch off. I think the last 3 questions all weren't marked properly, is that right?
Yeah.
And it sounds like when I talked to a couple people, they maybe weren't so clear on that. So the answer key is posted, all the right answers are up there. I really hate having a wrong answer on a scratch off. It's like the worst thing you can possibly do. It like totally reinforces people's lack of confidence in their abilities to do things, so I apologize. I'm really sorry about that. Answer keys are up. Please make sure you go through those. There is the one question I'll go back over. With the scratch-offs that were done marked improperly on my part, it's not Justin's fault, by the way. He doesn't make those. I make those, so it's all on me. I will try to figure out the most fair way to grade those scratch-offs. So we will try to figure out what to do with the questions. You guys probably know me well enough now that I don't just give away points if I make a mistake, but I'll try to figure out the way to make it fair, like it should be. So, Megan, you all right? You don't look all right. All right. Any questions regarding the exam? Justin is killer. He's almost done grading the exams already. So we hope to have them back to you tomorrow or at least or latest on Thursday so that you can use those to help you study for the final exam. Kirk?
I noticed this isn't about the exam, but on Sapling, where you have all the practice assignments for studying for the final, one of them is listed as being unavailable until the 14th.
Yeah, so it's the homework that's currently open.
Oh, okay.
So basically I want you guys to go through it for credit. Once it closes, then you can use that for practice again. I really don't recommend doing a homework that you just did over again, because it just means that you're like, okay, was I able to finally figure out how to answer that question? Let me try it again. If it's the exact same question, it's not a useful study tool. So honestly, I probably should not even include that last homework. The ones that you haven't seen for 2 months from the beginning of the semester, those are really valid study tools.
I had another question about Sapling. I don't know about for anyone else, but there was no pre-class quiz.
There's nothing.
Yeah,
There's nothing for this week other than a couple chem tours.
Thanks for letting me know, guys.
And
We just assumed since it was the last week.
No. No.
like
I was really hoping that that's what it was.
So I'll take a look. Thank you. Expect there to be pre-class quiz for Thursday. I'll go back and look and figure out how to make sure they're all on the same page. If you ever, I know we have like one more day together, but if you ever see something that doesn't seem right, just send me an email. I make mistakes. Have you guys noticed? I'm a regular guy who just has the luxury of a cool job where I get to work with you guys.
I didn't think you were going to fix it an hour and a half before the class.
So you didn't want to call yourself out for just trying it an hour and a half before class?
I sit out there the 2 hours before class and do it then. I'm not going to hide that.
So do we have a homework assignment the day before the final?
There's a homework assignment that's open right. Is it open now? Yes, there's a homework assignment that is for the material this week, so you can practice before the final exam this Monday. And I will make sure it's open by the end of the day tonight. Sounds good. Yeah. There's always a homework assignment and a post quiz. So yes. What day should I open the post quiz?
So wait, the day is on the same day as the final?
I'm asking a question. What day would you like the post quiz to be open?
Sunday.
Should we open it Saturday?
Yeah. Saturday, yeah, not Monday.
So if you want to study ahead of time, I'm not trying to say that you should finish the homework Sunday night and then the exams Monday, right? That it would be smart to work on it before then. That's just the absolute last time that you could finish it by. So the post-quiz, I'll have it due in the before the final starts. But I'll open it Saturday morning or Friday morning. What do you guys want? Yeah, it will be open all weekend. I'm just saying, when should I open it? Should I open it Friday morning? Would anyone do it Friday? Okay, so if you don't see that by the end of tonight, send me a reminder email. Open the homework assignment and post-quiz Friday morning to Monday. Just promise me you guys do it by yourself. That's usually why I don't have it open for multiple days, because that increases the chance that people will feel like they can share with other people what the quiz was on and help them through it. It has to be done on your own. That's the reason I typically don't do it, but I think that you guys can do that for the last one. Questions? All right. I appreciate you guys' patience. So, if we're going all the way back full circle, your workshop on Friday started talking about Gibbs free energy, looking at the Gibbs free energy diagrams, and today in class we're going to be working with those. So if a reaction occurs spontaneously in the reverse direction, what does that mean about the sign of Gibbs free energy? Okay, so why are we all in agreement that it's not B? Almost. What does the Gibbs free energy of 0 tell us? What's that, Taylor? Hannah, you want to add to that? Gibbs free energy equals 0 means we're at equilibrium. It means Q equals K. So then the question is, what is the sign for a reaction that is going to go forward in the direction it's written? Usually we say a spontaneous reaction has a Gibbs free energy of what? Positive or negative? I hear positive, I hear negative, I hear positive. It's negative. So the sign of Gibbs free energy tells us whether the reaction is spontaneous, but here's the part that usually don't talk about in bio class, is that it has to be negative Gibbs free energy to go in the forward direction. That means that it really matters which way we write the reaction. If we're going from glucose to CO2 and water, that reaction would be spontaneous for combustion, but that means that the reverse is opposite of spontaneous. So this reaction is saying, for the reaction to be spontaneous only in the backwards direction, what would the sign of Gibbs free energy be? Click in your new response. So read the question really carefully and then come up with your decision. Closing out. Does anyone not have a clicker today, by the way? I actually have a couple extras today. Everyone has theirs? All right. So we shifted in the right direction. So the sign of Gibbs free energy tells us if it's other than 0, it means the reaction will happen. If it's a negative sign, that means that reactants are going to become products. If the sign of Gibbs free energy is positive, it means the reaction will go from reactants back to products. Do we need to answer this question? Kira?
Can you just rephrase what you said? Because you said that when it's negative, reactants will become products. But you said if it's positive, reactants will become products.
Did I say the same thing twice?
Yeah.
So then which is right? So which?
If it's positive products, you have reactants.
Yes,
If it's
thank you.
negative reactants, you have
You know, sometimes you're thinking like 2 things ahead of what's going to happen next, and you say the wrong thing. Yeah. Right. So Gibbs free energy is positive, means the reaction goes backwards. So my goals for you guys today is for you to be able to predict the spontaneity of a reaction, which direction it goes, as well as if it is spontaneous, by comparing Q to K. And then we're going to be talking about standard versus non-standard conditions. I think you guys have already been exposed to this in workshop, so we're going to be applying that. And then from Gibbs free energy at standard conditions, draw an energy minimum diagram, predict where Q is, and then in class on Thursday, we're going to start talking about going back to some of your microbiology, metabolism reactions, finding Gibbs free energy, trying to predict if a reaction is going to happen or not, and talking about driving one reaction forward that's not spontaneous by using a reaction that is spontaneous. So let's go way back to exergonic and endergonic. These are terms you probably use in Bio 207, maybe not so much since then. So which of these graphs shows an exergonic reaction? Brianna, what would you say and why?
I said the right graph.
Why? What does it mean, exergonic?
Exergonic to me means that it's releasing energy into the system, and because the energy of the reactants is greater than the energy of the products, that's what I felt would be exergonic.
So exer comes from outside, means exo. So in my head, for some reason I picture an exoskeleton. Exo means outside. So exergonic means outside to the energy, so the energy goes out. So I totally agree with you, and I think the same way. And so what that means is that we can say that this reaction on the left is non-spontaneous. Takes energy to go. This one is spontaneous in the reaction in the direction that's written. So the left one is endergonic, means it takes energy to drive this reaction forward. And the one on the bottom means that it is releasing energy going the direction it's written. So if we go back and we look at our graph that we've seen over and over and over again throughout the semester, on the left side when we talked about kinetics, that is the part of the graph where we're at non-zero Gibbs free energy, that the reaction is going to be proceeding towards products. And on the right side, that shows Gibbs free energy is equal to 0. Just trying to show it a few different ways about when we're at equilibrium and how that relates to change in Gibbs free energy. So let's look at an example. If Q is larger than K, which one of these answers makes the most sense? Question number 7 on your worksheet. So, Kirk, why are you laughing?
Because I noticed that the front half of this sheet had the in-class worksheets, the front half of the workshop handout that we got on Friday.
Okay. So part of it's that. So we're reiterating some of the stuff you guys have already seen. And the other thing you guys are laughing at? The answer's up there. Animations. Okay. So, Alex, you want to summarize?
A reaction proceeds
Spontaneously.
Spontaneously to the left. Q is greater than K.
So what does that mean? So which one of these answers fits well with that then?
C.
Why?
Because Q is larger than K.
Does everybody agree?
Isn't the forward direction to the right?
Okay, so if we write a reaction, we have a reaction from the left, products on the right. So if the reaction goes to the right, it means that it's going from reactants to products. So if Q is greater than K, if that ratio is greater than K, does that mean we have more products than we should for that ratio, or does it mean we have more reactants than we should for that ratio? It means that this number at the top is bigger, and this is smaller than K, then we find a K. So that means that in order for this reaction to get to equilibrium, it would mean we need products to go back and to form reactants. So what does that mean as far as spontaneous in the direction written, or not spontaneous in the direction written? Spontaneous in the direction written, answer C. What does this mean? Is it going from left to right or right to left? In the forward direction means it would be going from reactants to products, and that's not what happened. It's not at equilibrium, because Q would equal K. So the reaction is non-spontaneous to go forward. So it's a little concerning that we were 50-50 even with the answer up there. Where did I lose you guys? What was confusing about that one? So I think it was it not the same as question 7?
Not exactly. Like the answer is that C says it's spontaneous in the forward direction, and this just said spontaneously, but then when we wrote a reaction for C spontaneously to the left, I just got confused.
Okay. So was it the idea of the wording on the worksheet? Where am I losing you guys?
I think people put C because it says, in that little box, it says spontaneously, and it says Q is greater than K. The question says, if Q is greater than K, so they looked at the answer that had the word spontaneously in it.
So, and then missing this part. Is that important? Yeah, it's kind of important. So, spontaneously to the left versus spontaneously to the right. So what would delta G, what would the sign of delta G be for this reaction? Talk to your neighbor. What would the sign of delta G be for this reaction? Positive, negative? So spontaneous to the left means it's not spontaneous in the direction it's written. It means it's spontaneous opposite the direction it's written.
I just looked at the equation.
That works? All right, so what do you guys think? Delta G is positive, raise your hand. Delta G is negative, raise your hand. Okay, does anyone want to argue their case on either side? Don?
You're saying it goes to the left, which means it's going from products to, never mind, it's positive, I read the wrong one.
Okay, so if we were saying on the last slide that when Gibbs free energy is greater than 0, that means the reaction is spontaneous in the backwards direction. This is saying that this reaction will go in the backwards direction when Q is greater than K. Questions? So we're going to talk about quantifying that. And I think that's the next slide. So if this was a particular reaction that we saw, and I don't want you guys drawing on that one that you have necessarily yet. If you guys look at the graph that's up here, how would we draw Q is greater than K on this graph? I want you to think about it, and then I'm going to ask you guys to draw it on my tablet. So where in this graph is K? Think about where Q would be if Q was greater than K. Talk to your neighbors, try to figure it out. Dana, you're going to draw this one. So I want you to write where K is, maybe with a star. And then write K above that or below that.
Where would Q be?
And then you need to decide where Q is. You want another color?
Larger than K.
Yeah, there would be more.
You can use your team to help you.
Okay. If Q's larger than K, then there's more products. So it's to the right, right? Remember, it's different worksheet. Is that good? I've never wrote on here.
So you guys can actually use one of your graphs to do this if you want. Just draw it out. That's what there's 3 graphs for. Looking at this.
I know, same, especially because I wrote it. And I have to explain it. But I think that's what I would have done.
All right. Dana, can you go ahead and explain what you drew up here?
In Q's larger than K, there's more products.
Okay, so how did you find K?
I just like remember it from, I don't know how I knew that was K, I just.
Can someone help describe? Brooke, can you help explain why we would know that's K down there?
Isn't that like right in the middle, it's like where it's at equilibrium, like right in the lowest?
Careful, is it in the middle? Middle is right here.
The lowest point.
You want to add to that? Chase?
I was just gonna say that K is the equilibrium constant, so where you're at equilibrium is where you're at the lowest energy.
So it's where you have the most stable mixture of reactants and products. That's where you have the lowest Gibbs free energy, and that's where you find K. So we could calculate K from this. Depends on how many reactants and how many products, but we can estimate that is this greater or less than 1? What do you think? Are there more products or reactants? More reactants because we're closer to the left side. So that means that the K is going to be more on the denominator than the numerator. So that means it's less than 1. And then how did you draw the blue line? Can you say that again, Dana? So Q is greater than K means there's more products compared to reactants versus K. So that means it's anywhere to the right would have been fine for this problem. Any questions on how we would draw? Sabrina?
Wait, so anywhere to the right of K would have been.
For this problem where Q is greater than K, then we can do that anywhere to the right. So honestly, if we had Q here, that would have been fine too. So Q is very close to K in this case, and that changes how much spontaneity there's going to be that occurs. And so we're going to talk about the magnitude of that in just a minute. All right. So we can actually quantify how much Gibbs free energy is available, because we're going to talk about how Gibbs free energy is used to do work. The more Gibbs free energy is available, the more work can be done. So here's an equation that comes from the ideal gas law, kind of through a whole bunch of manipulations you guys can read about if you really want. We're not going to get into them in class. So what I want you guys to do is I want you to take this equation and I want you to rewrite it using the rule of logs so there's no fraction. I think that's question 4 on your worksheet. Rewrite it so it's minuses and pluses, no division.
Oh yeah, I gave this I know it's going to be subtraction. I know it's going to be subtraction.
All right, Javante, what did you decide is another way to write this?
Delta G equals RT ln Q minus RT ln K.
Great. So if you have natural log of a fraction, you can do whatever is multiplied there times natural log of Q minus the natural log of K. And so you could either do that together, right? So the two ways we can kind of think about that, or the cleanest way I would say is RT ln Q minus ln of K. Right, that's how we unpacked that division. And then that means it's RT ln Q minus RT ln of K. Everyone okay with how those two things are the same? All right, so we're going to be talking about how big Q is compared to K. So let's we actually have written out here? Let's go ahead and estimate the value for K from this graph that you guys have on your page. About what numeric value would you estimate for K? Same graph. So type in a number. Type in an estimate.
Like percentage?
No. K. K value. What are you guessing?
Am I doing it from like energy or percentage?
K. What is K? How do we find K? Concentration of, right? So,
Okay, it's working now because you're right here.
bring the mechanics. All right, what did you guys say? Closing out. Is that there are two answers I disagree with here. Which two would I disagree with? 10 and 25. So the only ones that are wrong are the ones I've highlighted. So really, what we should do then is highlight the ones. The problem is I can't highlight the right ones because they're all off the screen, right? It's like musical keys. Okay, so all we should be able to say from this is that K is less than 1 because we have more reactants and products at equilibrium. That means that the reaction lies to the left. So, I feel like this is going to bore you guys, these 3 questions. You guys agree?
Yep.
Okay, so how can we answer these 3 questions? You guys know how to answer them? I want you to go ahead and finish answering those 3 questions that are right below the graphs. Use the graphs to draw Q bigger than K, Q smaller than K, and Q equal to K. Show what that would look like for those 3. So that's questions 6, 7, and 8, and then use the 3 graphs to represent those 3 cases.
You said that it doesn't matter what you put for this because Q is smaller than K, right?
If Q is less than K, then it would be anywhere to the left.
Yeah. Okay. We're talking. No, I mean K. We were estimating K.
So if K was 1, where would the minimum of this graph be?
It would be like this way, but I'm like
somewhere.
yeah, I'm like kind of relating it back to the exam. Like it was this was the answer rather than like K equals like 1 times 10 to the negative third, like really far to the left.
All right, guys. So when Q is smaller than K, well, come back to it, talk class. So if we have a Q smaller than K, where is Q going to be? Sarah? To the left of the minimum, left of K. All right, so that's going to be way over the side. If we have Q is equal to K, then where is that going to show up, Mia?
Right on. Okay. The same size.
That doesn't work. I think my graph shifted. Yeah, I agree. I'm wrong. Sorry. Error. Yes, I completely agree. So I would undo that. I would say that Q would be right at the minimum. Okay? Any questions on how we see where Q is compared to K? So one thing I want you guys to reflect back to, I really want you guys to remember that at equilibrium, K does not equal 1. At equilibrium, we don't have an equal concentration. What does equilibrium really mean? Q over K is 1, and Javante?
Isn't it that the
Yeah, the forward rate and the reverse rate is the same. So that means we have no more net change in reactants or products. Great job. All right. So I want to do one other thing. So let's close this out. Let's go. Why is this not responding? Go back. Go back. Why is nothing happening? All right. So what we're going to do, Thomas, you have a question first?
Yeah, number 6 on the worksheet. You're like writing through
Number 6, which is what?
K smaller than K, should we say
Spontaneity. You're spontaneous. Spontaneity.
spontaneous of the reaction?
So let's do this numerically. That's actually the next thing I was going to do. Is delta G equals RT ln of Q over K. Or RT ln of Q minus RT ln of K. I want you to answer Thomas's question. I want everyone to try to do this. When, what did we say? Q is greater than K or Q is less than K? So when Q is less than K, I want you guys to use this equation to answer Thomas's question. So try to use either version of this equation is fine. But mathematically, what would we be calculating? You guys know what I'm getting at? Use the equation where Q is one number and K is a number that's bigger than it, and then see what your value for delta G would come out to be. What's that? Yeah, but I want you to see mathematically why. Yeah.
In this equation, what is R? Because I know we've used a couple different. So that's the 8.31.
Depends on what unit we're using. If we're looking at energy, then it's going to be in joules. So there's a one that has joules in it. And that one has 2 more days. 2 more days. Dan, you want to share with us what you did here?
I just said it'd be negative. I didn't put any numbers in, I just said that Q is less than K, which is a smaller number, impacting a bigger number.
Okay, so you used the equation on the right. Is that what you're saying? Okay, that's what I wanted you to share, is how you did this. So you did use some numbers. So basically you're saying that if we have R is our gas constant. What's T? It's our temperature. And then Q would be some smaller number. K is a bigger number. So if we take a smaller number minus a bigger number, we're going to have a negative value. This is how we can quantify it. So what about using this way? Did anyone use the left one? Jose, how did you do it?
Well, ln of smaller q over bigger k is the negative number, and the negative times the positive is negative.
Great, so if you do natural or any log of a number smaller than 1, then that gives you a negative value. Just like the Henderson-Hasselbalch equation, if you guys remember that. Having a log of a fraction that's less than 1 gives you a negative value, which means your pH is less than the pKa. The same exact thing applies here. So that means our Gibbs free energy is going to be negative if Q is less than K. So I really don't want you to memorize. I saw a whole bunch of people writing down, if Q is greater than K, then don't memorize that. Just think about where you are in the graph, where we're going to go to reach equilibrium. You can use this equation to double check it if you want. So then we're going to talk about using Gibbs free energy as a driving force. The bigger this number is, the more non-zero it is, the further away from 0, the more we can use it to do work, or the more work is required to make it go. So how do we make delta G as big as possible? Do we try to make Q and K as close together as possible? Why far away?
Because then you'll either release a lot of energy or you'll store a lot of energy.
So if these two are extremely different, it means that in this case, so if Q is smaller than K, if Q is really, really, really small and K is really big, we're going to end up with a giant negative Gibbs free energy. It means we have a reaction that's really spontaneous that can go. All right, so let's go back to our question here. Killing me. All right, 5 more seconds, close it out. Today's my best moment in class this semester, I gotta admit, no mistakes at all.
People still got it wrong. Looks like the graph is right.
All right, so let's go back. Let's go back and let's talk about it. On Friday, you guys, and last week too, you're talking about standard conditions, right? Do you guys remember what your concentrations of metals were? Sarah, stop. Do you guys remember what your concentrations of metals were last week in your electrochem lab? Were they 0.1? Were they supposed to be 1? Okay.
There was one that we had.
So, did we have standard conditions last week in lab? We did not have standard conditions. What are standard conditions? That I meant to have up here, right? So, at standard conditions, anytime we have this little not symbol, that means we're standard conditions, which means we're at room temperature. We have 1 molar concentration of everything. Does that seem like most reactions are always at 1 molar? Does that seem a little arbitrary? So let's keep in mind as we go forward that this is a really, really arbitrary value, but it's a way to standardize things. It's like saying sea level is at the sea level because it's a number that's easy to talk about, and we can say, well, how tall are buildings or how deep are ocean trenches? As long as we talk about from the same frame of reference, it doesn't matter if we're in Asia or if we're in Africa or we're in the US, sea level is still the same value. So we're going to compare, we're going to reference everything back to standard conditions. So that means that if we have standard conditions, that means our Q is concentration of products over concentration of reactants. But we're at standard conditions, so everything is 1 molar. So we have 1 molar, doesn't matter how many coefficients, what we're raised to, the stoichiometric coefficients are. Our Q is always 1. So then what does this equation become at standard conditions? I want you guys to rewrite this equation for delta G naught. So rewrite the equation, but instead of being delta G equals, write delta G naught equals. So question number 9.
No, I would not use like not equals.
So 1 molar was the standard condition, so we compared it to non-standard. Okay. What are you doing?
So would it just be 0?
So I want you to rewrite the equation in either form. You can either use this form or you can use this form.
You say not equals.
So delta G naught, that means at standard conditions. So what's different in standard conditions? Or what's known in standard conditions? Okay, So write this equation again. Write Q equals, so put 1 in place of Q. And then simplify that down.
Does it?
All right, so take another 15 or 20 seconds.
Bring it to studio tomorrow so we can check this.
All right, so Brian, what do we notice about the equation once we do it at standard conditions, or delta G naught?
Alright, so our Q is 1, which means that everything times the ln of 1 would be 0, so it would be 0 on one side, and it'd be negative RT ln of K equals the change in G naught.
Okay. So what we're doing is we're comparing it to sea level. We're comparing it to that standard condition. So we're saying the change in Gibbs free energy for a particular reaction, we're going to say that that's equal to minus RT ln of K. And so this seems a little arbitrary, but I'm going to kind of get into why this is really useful for us as chemists. So let's start off with this question. We'll kind of frame it for us. If delta G naught is positive, what does that tell us? Shows me what percentage of people have clicked for each answer. All right, you guys don't agree with each other necessarily. I want you to try to convince the person next to you of why you chose the answer you did. If the person agrees, turn to the other side. Got worse.
It always does. Every time you have a stage
So Taylor's question's good. So Taylor asked, is it standard questions and then at standard conditions, and Megan said. Okay, so delta G naught, that's at standard conditions. If Gibbs free energy at standard conditions is positive, what can we say about the reaction? Does anyone want to help clarify this mess of we don't know? Why?
Because that's the only way you can get a negative K value is a decimal. The ln of K, the only way you get ln of K is negative to the decimal.
Okay, so you're going back to the equation, this one at the top here, is that right? So you're saying that if this is positive, ln of K has to be negative, because a negative times a negative gives a positive. Okay, so that's one way. So that means that K would have to be less than 1.
Yeah.
Okay, what's another way we could do this? Thomas? So I think that you're on the right track. I think you might have flipped something in the middle, though. Taylor?
At first, I was thinking that Q, like you said, Q is greater than K because it's positive, but now we're, like in the equation at standards, there's no Q.
There is a Q. What is Q? Is Q 0 or 1? Standard conditions is 1. So let's go ahead and let's draw that. So we're going to draw our Gibbs free energy diagram. We're going to draw out where our Q is. Where's Q? If Q is 1, where is that in this graph?
Dead center.
Right down the middle. Okay? And then we're saying, to get from Q to K, is the reaction spontaneous? In either direction. Is it spontaneous in one direction or the other?
Spontaneous in the reverse direction.
It's either in the reverse or the forward, because if it was at equilibrium, what would delta G be? 0. Okay, so delta G naught is not 0, so that means that we are either it lies to the left or to the right. It doesn't lie right in the middle, right, Demetrius? So then if it's delta G naught is positive, what did we say in the very beginning of class? If delta G naught is positive, is the reaction spontaneous in the forward direction or the reverse direction? So that means to get to equilibrium, this reaction would need to proceed to the left from a Q value of 1. So Thomas, I think, kind of worked what you were doing, but then somewhere in the middle it got flipped from which way it was going which way. Kirk?
So for the way this question is worded, like for response C versus the reaction lies to the left, is that the right answer? Because are you saying, does that mean that it's going to move to the left to reach equilibrium, or are you saying that Q is to the left, which is not?
So if the reaction lies to the left, we've only used that to talk about where K is. So this describes where is the most stable mixture of reactants and products. It lies to the left, meaning it lies towards more reactants than products. So at any standard conditions, Q is always going to be 1. So then why would we want a table full of Gibbs free energy values of standard conditions? How would that be useful? What takes up less space, maybe? Go ahead, Taylor. What takes up less space, drawing this out or saying a positive delta G naught? It's a little bit shorthand way of saying that the graph lies to the left. And the question is, well, how far to the left? And that's going to tell us the magnitude of delta G naught. So whenever you look at delta G, I don't want you thinking, oh, this reaction is spontaneous or this reaction is not spontaneous. You can say, well, if we look at standard conditions, we know it lies to the left or lies to the right. So that standard conditions is really deceiving, and that's what we have to keep referencing back to. But we're going to do some calculations on Thursday where we say, well, we're not usually at standard conditions. So this is our reference point, and then once we know what this graph looks like, we can say, well, in the brain we actually have all reactants. So what's going to happen to get to equilibrium? So we'll know what this graph looks like, and that allows us to do some calculations. So let's take a look. So I'm going to post these slides after class so you can kind of get all these little tidbits. We're really going to be paying attention to the magnitude, how far away from 0 Gibbs free energy is. And that's going to tell us how much energy is needed for that reaction to proceed or how much energy it can yield. So let's tie this all back into biological examples. If we have a reaction that needs to go forward, it's an endergonic reaction, that to make this reaction happen, so we're showing the analogy of pulling a block uphill. That reaction is not spontaneous, and in fact, if we snip that rope, it would be spontaneous in the reverse direction. So the question is, well, how do we get this to go forward? How do we get that to move? Kira?
We just supply energy for it to move.
How do we supply energy to make it move?
Well, like in this case, with the block, you have to like hold the string or whatever it's like connected.
So how would we do that? What's a way we could do that? What might we tie it to? What might this be connected to? Pulley. And then what's on the other side? What if there's another reaction on the other side that has the same or greater amount of potential energy that it's going to give up in order for this one, when this goes, it's going to drive this reaction forward? So that's kind of how biological reactions work. Is we take a reaction that is very spontaneous in the forward direction, and we use that to drive reactions that are non-spontaneous. So for instance, the formation of glucose in photosynthesis. That reaction requires a whole bunch of energy being input in order to drive those reactions forward, and we store it as glucose. Or when we then consume glucose, that then releases energy, and we can use that to drive other reactions forward.
So is it less, or does the reaction have less potential energy if it's not as steep of a curve of a triangle? In this case, like if the hill wasn't as steep.
Yeah, so what we're kind of getting at is that the steepness is not really where we would want to focus. It would be the magnitude of the block, and hence the force. So the bigger Gibbs free energy is negative, the more mass would be over here, the more it could pull in this way. Does that make sense? You got a chance to click in? All right, so the idea is that the more, as Don was kind of getting at, you could either represent it a couple different ways. I guess we could represent the same block size but steeper slope. But the way that this figure represents it is that the bigger that block is, the more Gibbs free energy would be available to do work, and hence the more work we could get done. So the magnitude is really important here. So let's talk about this as far as coupling reactions together. If we couple these reactions together for the reaction that's shown in that second line, or the A goes to C plus D, is this set of tethered reactions, is that overall reaction spontaneous or not? So is that first reaction spontaneous? A goes to B plus D. If we have one molar of every so what happens if you combine the two reactions? Yeah, you're right. We get the reaction to show A goes to C. It's still going to be negative because you're still going to because if you see C is like. So how does that work? So use the pulley down. So it's going to be less. What's your logic? All right, does anyone take a stab at explaining their thought process to answering this question? Anyone who hasn't been talking too much yet today? Chase, you've been relatively quiet.
I said no.
Why?
And the reason would be because of standard conditions, we know that Q is equal to 1. And with that reaction, delta G naught is a negative number when you add them. And since Q is 1, it lies to the right of.
Okay, so I think you're saying some things that are valuable. I think that there might be a little bit of confusion. Thomas, you want to ask it? Or
since that standard conditions, that means that Q is 1, and if you plug that into the equation of the report, that means that delta G is negative.
okay, so I think you guys are kind of like jumping right to a number at the end. Val?
I said yes, and I don't know if this is legal, but I just added the two equations, and the B is on opposite sides, so it cancels out, so then you get the end product of A.
Okay, so let's look at what you did here. So if we have A is being consumed to make B and C, but then we have another reaction that uses B to generate D, then what you did is exactly what I would do. And then on the left side we have A, on the right side we have C plus D. You can really add together reactions like that. Then we can do the same thing over here for the Gibbs free energy. So what did you find for the difference, or the sum of those? Kilojoules per mole of A that are used. So how else can we think about this? Cosme?
K bigger, what, negative RT ln of K is equal to delta G naught.
So K is bigger than what?
Q.
Okay.
And we said that before, if Q is smaller than K, then it's spontaneous.
Okay, so you're saying that based on this number, is that what you're saying? That the reaction lies to the right? So we need to be a little bit careful because it's a K of a combined set of reactions, but I think that's a valid way to think about it. Kira, what were you talking about as far as, I think you were thinking about Le Chatelier's principle, right?
I think so, but I don't think I was thinking about it in the correct way.
I disagree. So is this first reaction spontaneous? A going to B plus C?
No.
Nope, it's spontaneous in the reverse reaction. So this reaction doesn't want to go. So how do we drive it forward?
You have to either add more reactants or you can add more energy.
So if we add more reactants, we're changing Q, which is legit, and we can move Q to the far side of K, meaning we drive it towards products. Or what was the second one?
You can add more energy.
We can add more energy, or what's another way?
You can take away.
Take away products. So how do we take away products for this reaction? What do we take away? Maybe let's get rid of some of the B and use it to generate D. So if this reaction is spontaneous and it consumes the product, B, to make something else, we can see that the second reaction is spontaneous, the first one's not, and so we basically, by having B as a reactant for the second one and product for the first, that's how we tether these two reactions together. So the one that drives this forward is the one that's spontaneous. It uses up products as soon as they're made. If they're made, just a little bit of them, then they're going to be used for the next reaction, meaning that Le Chatelier's principle really comes in here. So I like the way that you thought about that. So there's a number of different ways we can think about it. The simplest one is we add up the two reactions. What's on the left side, what's on the right side. We find what the change in Gibbs free energy is overall, and we know that now the Gibbs free energy change at standard conditions is negative, meaning that K is to the right. The reaction lies to the right of Q. We're going to generate products. So yes, it's spontaneous at standard conditions in the forward direction. Questions? I'm trying to describe lots of different ways we can think about it because it's not a single way to do it. These questions are really simple in some ways, but they have multiple levels of descriptions we can go into. Alex?
Look at the graphs of what the spontaneous and non-spontaneous delta G naught.
Do you want to draw them out?
Yeah.
Or you mean the ones that you had at the top of the page?
Yeah, the top of the page.
So that's for you guys to draw on your own.
But aren't they different than the ones on the front?
Yep, they might be. So if we have standard conditions, where's Q? In the middle, and then you have to decide if Gibbs free energy is positive or negative. Does the reaction lie to the left or the right? And then you need to draw that minimum. So I want the shape to be appropriate, where the minimum is to the left or the right to be appropriate for that question at the top of the back of the page. But I don't care about exactly where it is. That's fine. Okay, so we're talking about for a coupled series of reactions, we're looking to find the overall free energy, and that's the sum of the individual steps. So this is what glycolysis is all about, is taking individual steps, some that are spontaneous, using those to drive reactions that are non-spontaneous, consuming products of one reaction to make a non-spontaneous reaction go forward. So how does this all relate back to electrochem that you guys did last week? Does anyone know the relationship from Gibbs free energy to E cell? Taylor?
Not really, but I know that whenever you see like we had kilojoules and kilograms,
And electrons have some sort of energy. So once again, here's one of these things being Gen Chem. The last week of classes, we're not going to go into deriving everything, but we're going to talk about that the spontaneity of a reaction in standard conditions is directly proportional to what the electrochemical potential of a cell is. Faraday's constant is how that proportion is played out. And then what is this N? Number of moles of what in this case? What was that, Katie? Number of moles of electrons. So in a particular electrochemical cell, if we have 2 electrons transferred, that will be our N. F is Faraday's constant. And then E cell tells us whether a reaction is spontaneous or not. What's the electrochemical potential between two different things? You guys measured that in lab last week. Was it always E cell at standard conditions though? No, you measured some at 0.1 molar, some at 0.01 molar. So some of that was and some of that was not. Here's our Faraday's constant. There's 2 different sets of units you guys can use. I'll obviously give you this on the final exam. Everyone want to write those down so you have them for some calculations? 96,485 joules per volt times moles. So what's another way of saying joules per volt? What is this big C? Anyone know the electric constant, or what's it called? Coulombs. Yeah, Alex. All right, so 1 coulomb is equal to a joule per volt. So either set of those units might be useful in the next couple of days in class. All right, so now let's put this all back together. So you guys ready to do some manipulation of equations? Just like we found the Henderson-Hasselbalch equation, I want you guys to derive the relationship between all these different equations that we have. You guys ready? Okay, so here's these 2 equations at standard conditions. I want you to solve E cell. So get E cell alone in terms of natural log of K. Go. I want you to rewrite. Use these equations, these 2 equations, to have E cell equals, and then something in terms of ln of K. Same thing, right? I want you to write E cell. All right, guys, bring it back together. So, mommy, what's the first step we do? What's them? Great, so we know both of them equal negative, or delta G naught, so we can make those two things equal to each other. So, RT ln of K equals minus NF E cell at standard conditions. And then what would you do? Yeah, there's a negative on the left side there. It's there. You just can't see it.
And then we divided the negative cell over negative RT.
Okay? So when we do that, see the negative was there. It's just gone now because it's negative divided by negative equals a positive. So E cell then equals RT ln of K over NF. And I wanted it to be in terms of ln of K. So ln of K I kind of put out separate there, and we'll see why in a little bit when we do some more calculations with this. Is everyone okay with this is the relationship between E cell and ln of K? RT. What's the problem?
If you do, I had RT ln of K all on the tops. If you write it like that, to me, it looks like you want me to do RT over NF in parentheses and then multiply by.
You can? Totally legit. Same thing.
Okay.
So you could also do ln of K divided by NF times RT. That's the same thing. Divided by 1, right? Because it's all on the top, all on the bottom. And the reason we're isolating it like this is because I want to try to start to draw your attention to the relationship between Gibbs free energy, E cell, and K. That those three are really intertwined. If a reaction is spontaneous at standard conditions, what is K? If a reaction is spontaneous in the forward direction, what do we know about K? K is greater than 1, it lies to the right. If E cell, what is E cell if a reaction is spontaneous at standard conditions? So if this is spontaneous forward direction, this is negative. That means that E cell is negative. So a negative E cell tells us a reaction is spontaneous in the forward direction as well.
So is it opposite of what I wanted to? Am I hearing that right?
So then if, at standard conditions, if this is negative, then that means that this is going to be greater than 1.
They're opposite. Okay.
So, if you've noticed, the reason that I wrote everything times ln of K, R, gas constant, T, standard temperature, right? Because we're at standard conditions, 25 degrees Celsius. N is the number of moles, and F is a constant. So what I did is I pulled out all the constants and separated those. And so we end up with a really simple relationship between E cell at standard conditions and our K. For any reaction, this holds true. If you go to a table in your biochemistry book, when you go to take biochemistry, and you look up a particular biochemical reaction, you'll find an E cell, E naught cell value. If you have that number, you can automatically calculate your equilibrium constant if you know how many moles of electrons are transferred in that reaction. You can automatically find Gibbs free energy at standard conditions as well. So what we're saying is that all three of these tie together really nicely at standard conditions. There's this little triangle that kind of helps show how they all fit together. Javante?
Okay, so I tried to do it like, I thought it was saying ln of K, like you wanted ln of K equal, so I don't know if what I did is right.
Okay, so we can take a look at that after class. So you could also do ln of k equals, but this is the more common representation, is E cell equals something times ln of k, and it's this 0.0257 volts divided by the number of electrons times ln of k. So if you know ln of k, you can find E cell at standard conditions. If you know k, you can find Gibbs free energy at standard conditions. Taylor, you have a question?
You just wanted to see, make sure that the 8.314 joules per mole, that's for like every mole. So say if there was a mole of oxygen, that's how many joules would be in it?
Yep, so that is per mole, and then N is the moles of electrons. So we have that kind of wrapped up in there.
Okay, so say if you have like the N and you're doing calcium and there's 2 electrons exchange, then it would be negative.
Then you would have 2 for your N, and that should account for calcium being 2 electrons transferred.
So it's not about the moles of
The moles of electrons that are transferred. All right, guys. So this is why we've been doing all this. Is now we look at a set of reactions like this, and it makes Miss Terrell very happy. We can zoom in to any one of these reactions, and we can predict whether it's spontaneous or not, how much driving force is needed to push it forward. Do you think this first reaction is spontaneous? Glucose breaking down into glucose 6-phosphate. Why do we think that that's not a spontaneous reaction? How do you know we need energy to drive it? Okay, so I hope you guys all notice what Shane's pointing out. On top of this reaction, it's not going by itself and making ATP. It's going only because ATP is cleaving to ADP, and that's driving the reaction forward. So I want you guys, the last thing we do in this class today is I want you to go ahead and determine what K is for this reaction. Determine the equilibrium constant for the hydrolysis of ATP to ADP in phosphate water. Getting ready to inject it. Is there something you guys, a number you guys need, or you can look everything up? So R is up on the screen. It's 8.314 joules per mole Kelvin. All right, so we're basically out of time. Let's take a guess. Is K greater than 1, less than 1?
Less than 1.
Why would it be less than 1? So we have delta naught. Gibbs free energy at standard conditions is negative. That means the reaction is spontaneous or not from Q is 1. Is the reaction going to be spontaneous in the forward direction from a Q of 1? Delta G naught is negative. What does negative tell us for delta G? Spontaneous in the forward direction. That means that K lies to the right. Is that what you guys are thinking? K is greater than 1. All right, so why don't you guys work on this? We'll start class out with doing the calculations. We're over class time. Stay dry, stay warm. I'll see you guys on Thursday. I will open the homework so you guys can practice.